I'm Blake. I'm a principal engineer at Cisco, and I'm going to be talking about some work that I had been doing with my colleague and boss, David McGrew, who's a Cisco fellow. So to get started with a little bit of motivation, I don't want to minimize the value of DNS layer visibility and enforcement, DNS layer security in general, because it's super valuable and it's generally a really efficient way to doing that first level effort of securing your network, which is one of the reasons why everyone kind of does it. But at the same time, it's not perfect, and this actually kind of flows with some of the questions that I saw in chat and some of the topics that were discussed in the initial keynote. So I think it's a pretty good fit for this talk. The two main ways that it's not perfect that we're going to be talking about in this session is number one, unsanctioned DNS. So when users on your network or machines on your network are going to DNS servers that you didn't configure, that is restricting the enforcement piece of DNS layer security. So you're no longer able to sinkhole malicious domains. The other side of DNS layer security that kind of lacks is some of the topics that were brought up in the previous talk, which is encrypted DNS. So encrypted DNS has a ton of advantages, and as a network security practitioner, it makes a lot of sense to have encrypted DNS, but encrypted DNS that you control. So when it's unsanctioned and encrypted DNS, so they're going to DNS servers that you don't control over encrypted channels, that's both removing the ability to do enforcement, and it's also restricting your visibility. So you're no longer able to implement a passive DNS system that gives you the visibility that you previously relied on. And I think we can all agree, again, DNS layer security is important. There's a ton of recommendations and guidelines presented by people like the DoD that say this is an important part of any kind of network security strategy or enterprise security strategy. So in this talk, we're going to give a little bit of background over DNS just to level set and some of these other issues, and then kind of quantify the problem and talk about how do we move forward. Okay, so to, again, level set really quickly, traditional DNS. I have a client. The client wants to go to some domain, bad.com, so he needs to know the IP address. So he talks to the recursive resolver that the enterprise has set up. The recursive resolver, talks to some set of authoritative named servers to get the IP address. They get the IP address. Again, this is a made-up IP address. And now the client knows how to connect to that bad.com server. So then it actually connects to the malicious server over typically HTTP or HTTPS and starts communicating. So that's kind of generally like how DNS works at a super high level, ignoring a lot of complexity. And now thinking about like traditional DNS enforcement, and we have pretty much the same kind of setup. So the client wants to query bad.com. It wants to get the IP address for bad.com. But the enterprise's recursive resolver, it has some threat intel feed, and it knows that bad.com is something clients on the network shouldn't be going to. So instead of sending the IP address associated with bad.com, it sends some IP address that the enterprise controls. And typically this is some kind of sinkhole setup where you can limit the exposure of any kind of malicious behavior that's happening on your network. So the client gets the DNS response to this sinkhole IP address, and then the client goes to connect to bad.com. But instead of the actual malicious IP address, it's connecting to the sinkhole IP address. So, this is a really easy way to do enforcement, to restrict any kind of, malicious C2 activity. And it's really easy. So, all you need to do is kind of hook up the recursive resolver to some threat intel feed, relatively easy. And then you have this kind of enforcement. So it's pretty nice. So the issue comes with unsanctioned DNS. So the previous DNS enforcement works really well when everybody adheres to the DNS servers that you say they should go to. But that's not always the case. And there's a lot of reasons for this. So the reasons that we've seen in our data, it's mostly around lab environments or unmanaged endpoints. So a lot of people that are setting up some lab environment quickly is just going to hard code some DNS server that may not be the DNS server that the enterprise is actually wanting everyone to go to. Virtual machines, users, so if there's ever a problem, and we see this a lot, if there's a problem with the enterprise DNS server, a user's going to change it to Quad 1 or Quad 8, Google's or Cloudflare DNS server just to get things working in the short term, and then they'll forget about it, and that will stay their unsanctioned DNS server until the enterprise corrects it. And then one of the other big issues here is that DNS configurations are moving up the stack. So, no longer are applications completely dependent on the DNS configuration of the operating system, but instead are starting to roll that, themselves, so that they have more, they're more robust against these DNS outages. So it kind of makes sense from the application's point of view and the robustness point of view. But again, that's kind of restricting visibility. And so, in this setting, the client is going to an unsanctioned DNS, which is Quad 1. It's looking at bad.com. Quad 1 is, they have a policy of doing very little filtering, little if any filtering. So when you go there, you're not going to get any kind of DNS layer security. So you'll get the bad response, and then the client will be able to go to that malicious server. And so that's the unsanctioned DNS point of view, where we're losing enforcement. But even with the unsanctioned DNS, we would still be able to get some kind of visibility if we had passive DNS infrastructure. So like we don't have enforcement, but we have visibility. But as kind of was mentioned in the keynote, there's a series of standards that have come out over the past 5 to 6 years that would also remove the visibility piece. And the three that I'm just going to briefly mention: DNS over TLS, DNS over HTTPS, and DNS over QUIC, which is one of the newest. And all of these, they have advantages and disadvantages. But from the point of view of network defenders, like I think one of the most important questions, like how easy is it to detect DNS going over these different encrypted protocols? And so there are a lot of assumptions here. So DNS over TLS, I say it's easy to detect. That's primarily because the actual RFC says that it should go over port 853. And for the most part, people adhere to that. So if it did not go over port 853, it would be much, maybe more difficult to detect. DNS over HTTPS. So this one doesn't have any easy network tells. So the default port is the regular TLS port, so TCP 443. The application layer protocol extension in the TLS client Hello is advertising H2 or HTTP 1.1. Again, this is like every other HTTPS session, so you're not getting very much information there. So detection here is hard, and what hard means is basically we'll need to rely on network traffic analysis to try to differentiate whether this is DNS or something else. And then finally, we have DNS over QUIC. So QUIC is a really new protocol that is basically HTTP3. So it's going to be presumably replacing a lot of the HTTP2 and TLS connections that we had in the past. It's still relatively new. And so with DNS over QUIC, I have easy with an asterisk because, again, it has the application layer protocol negotiation extension that says it's DoQ, but that can change. And the really interesting thing about QUIC is that it supports multiplexing like quite natively. So it could definitely be the case that you end up creating one connection to Cloudflare that will have your DNS over QUIC and all of your other connections. So you'll be able to get very little information. So it might turn out to be very difficult to detect DNS over QUIC. And I think the punchline for all of those different protocols is basically the same. We no longer have the ability to do enforcement, because presumably these are going to unsanctioned encrypted DNS servers, and our visibility is also lacking. So our passive, traditional passive DNS systems will not be able to give us the same level of information with the encrypted DNS connections. There's other ways we can get this information. I'll talk about that later, because at the end of the day, the client is still connecting to an IP address. And a lot of protocols will have the domain name that we can extract. The last thing I'll say in the not so brief overview and motivation is that there's definitely more widespread support for encrypted DNS. It's trivial with Firefox and Chrome that make up 95% of all browser traffic to turn this on. It's going to be turned on by default, if not by default already in both of those. So there's not really a technical hurdle to enabling these protocols per application, or even at the operating system level now, or at least very soon. So I'll quickly talk about a couple of real-world examples that I personally think are pretty interesting. In the first two examples of using DNS over HTTPS to I think it's quote unquote evade detection, because there are legitimate reasons for using DNS over HTTPS, and for a network defender saying evade detection, the other side of that coin is having robust network communication. So I'm not really trying to place a value judgment one way or the other here, but just to say there are these three tools. The first two were interesting because the source code's online, so you can actually look and verify exactly what they're doing. The crypto miner, nice hash miner, I think in its documentation it kind of brags about being robust to unfavorable network conditions. And one of the ways that it implements that robustness is by hard coding Quad 1 and Cloudflare DNS to do its DNS over HTTPS. So, the DNS at least is not the place where you can stop this crypto miner. The next is AdGuard Home. So, this is not necessarily malicious at all. Like, I think a lot of people use ad blockers and things that block trackers. I do. But it also hard codes the DNS server that it uses. So you can go into the source code and see this. So if you were to do something like, oh, I'm going to implement a DNS-layer block so that you can't look up DNSFamily@adguard.com, it doesn't really matter because it knows the IP address and hard codes the IP address, so it'll still be able to connect to that DoH server. The third example is maybe a little more interesting from a threat perspective. So UltraSurf is a censorship circumvention program that it has, again, some valid uses, but we also see malware using this not uncommonly. And it has a lot of really interesting evasive mechanisms in place, but one of the ones that we were relevant for this talk is that it does hard code a DoH server, and it uses DoH. And the malware that we've seen that leverages UltraSurf is, it's very clearly using DoH to evade any kind of detection. So that's a threat relevant example. Another example, and this was from a Talos blog, and I describe this as saying like using shared hosting to evade detection. And if you're familiar with domain fronting, another way to describe this is they almost want to use domain fronting, so they don't quite do domain fronting, but they're clearly setting up all of the pieces to use domain fronting. And so this relies on some cloud provider that hosts a benign site and will also host your malicious site. So in the example that they went over, the malware was looking up DNS, using the Cloudflare DNS server, the local DNS server, to look up some Myanmar government website that they knew was it was hosted on Cloudflare. So they got some IP address that's associated with the shared hosting that Cloudflare has, and with that IP address, they were able to send an HTTP request. But instead of the Myanmar government website in the HTTP host field, they replaced it with their malicious site in the host field. And so, this is an example where DNS layer security or enforcement is kind of lacking, because none of the DNS information is going to give you that IOC for the truly malicious site. And maybe the Myanmar website, depending on where you are in the world, will have low enough false positives to actually be a good indicator. But that's not really guaranteed, and that's not really the point. For this attack to work, any DNS request to any server that's hosted by Cloudflare would give you a correct DNS response. So I'm going to do a really quick shift and talk about some real world measurements. And I don't want to sound I don't want to be too alarming. And so giving you a sense of, like, when we look at a real large scale global enterprise network, like, what's the percentage of DNS requests that are going to unauthorized servers? And it's not 30%, it's not 40%. So what we see is somewhere between 0.2 and 0.4%, based on the time of the week. So it's not super high in terms of percentage, but when you think about it in terms of raw number of requests, when you're seeing 10+ billion DNS requests per day, there's millions, tens of millions of DNS requests going to unsanctioned, unauthorized DNS servers. So it's maybe not the end of the world, but definitely a problem that we need to be aware of. The one interesting thing about this this figure specifically is the cyclical kind of patterns that we see. And what we see is that during the weekends, when there's less user activity, the percentage of unauthorized DNS goes up. And that's mainly because most of the unauthorized DNS that we see is coming from labs or other non-user initiated traffic. And then one other really interesting picture here is the DNS enforcement in the real world. So we were lucky enough to have measurements before and after a DNS layer block went into place. So we were working with an organization. They wanted to block DNS-over-HTTPS, and specifically the DNS.Google server. And so the easiest way for them to do it, again, because DNS layer security is super efficient, was to put a DNS layer block. And so we monitored the traffic, the successful connections to DNS.Google before they implemented the DNS layer block, and it was somewhere on the order of 12 to 14,000 connections a day. And then we saw them implement the block on day 2 in this diagram, and then we got to see how many successful connections within their enterprise were going to DNS.Google after they implemented the block. And the interesting thing here is that the block only reduced the number of successful connections by about a half. So even implementing the DNS layer block did not really solve the problem of successful DoH connections to DNS.Google. And a lot of this is because of the previous examples where people were hard coding IP addresses, and DNS.Google has very easily, it's quad 8, so or 8.8.4.4, so very easy to remember, very easy to just type. And a lot of the infrastructure that we see is lab infrastructure where people just put it in there, and applications that just hard code it. And then the last thing in terms of measurements is just looking at the breadth of DoH servers out there. So, these are the top, I think, 20 or so DoH servers that we observed during October or November of 2021. So, there's definitely more popular DoH servers, but there's a really long tail. And during that time, we saw active, real connections to around 50 to 60 different DoH servers. And during our monitoring over the past year, we've detected a little over 300 DoH servers, and we see typically 5 to 6 new ones a week. So they're constantly being introduced, and we need some way to get a handle on that. So really quickly, I'm going to talk about some strategies that we can use to maintain visibility. And the first is kind of detecting encrypted DNS. So we want to have an understanding of what are the DoH servers that people on in my enterprise network, what are they using? And I think there's 3 broad techniques that people can use. The first is network traffic analysis, and this works pretty well. I think the slides are in the Discord, so you can take a go to this paper. It's a pretty good academic paper that explains some of the trade-offs of network traffic analysis to detect encrypted DNS. The second is network traffic tells, which is always great because you have this kind of ground truth, more or less. So TCP 853 for DOT, looking for different application layer protocol negotiation extension data within TLS, like DOT or DoQ. And then another thing you can do is look at internet-wide scan data. So we basically just ran a regular expression looking for the DNS query for HTTPS and Shodan data. And it's pretty straightforward. It gives you a long list of potential DoH servers. And the important thing here, and this is why I would say one of the reasons network traffic analysis does a really good job at detecting encrypted DNS servers, is because we don't need super high precision. So we only need high recall and a reasonable precision. And reasonable precision here is defined as like the number of positives that we can reasonably verify in a given day, which if you have a scanning infrastructure, it could be millions or even more. So there's a lot of tools. You can use curl. We have an open source program, Mercury, that probably going to be a lot of updates in the next week. We have a lot of code that we're about to push out, but it's open source. It has a TLS scanner that can specifically scan for DoH servers. And like I was saying, there's each week we identify something like 200 to 300 new encrypted DNS servers, and we verify 5 to 6. So we're constantly getting a new trickle of DoH servers. And then the last piece, really quick, is expanded domain name monitoring. So passive DNS is, basically we're looking at the DNS protocol to extract domain names and IP addresses to feed into our backend system. But there's really no reason why you can't or shouldn't be doing this to all of the other protocols. So I would say like an expanded passive DNS infrastructure where it's kind of domain name monitoring, where we're looking at HTTP requests, TLS client hellos, and less than TLS 1.3, TLS certificates, and QUIC initial packets and QUIC crypto frames. And all of these have domain names that we can extract and associate with IP addresses and associate with endpoints. So it's basically just, let's kind of generalize what we mean by passive DNS and apply it to all of these other protocols, which can be done efficiently. So that's the other piece. And then to conclude really quick, and kind of like I said at the beginning, DNS layer visibility enforcement, very efficient, kind of a cornerstone of most enterprise security programs. DNS maybe was never designed for those things, but it's definitely used for visibility enforcement and security. So, it's nice to have. But I think there are some drawbacks, and we need to acknowledge those drawbacks, and we need to move on. And basically, we need to minimize unsanctioned DNS. We need to ensure that all of our encrypted DNS is going to the proper authorized providers, your enterprise provider. Maintaining active intelligence on encrypted DNS domain names and IP addresses is a really important part as well. This is super important for a lot of the work that we do in network traffic analysis. And then, like I was just saying, augmenting visibility gaps by kind of generalizing passive DNS and applying it to all of these other protocols. And I think that's it.